So we've talked about the total potential in kind of theoretical terms, but let's just do a quick little problem to show how we track potential in a flow problem. So let's suppose that we have a water column here, or a soil column. So here I've got some water that's sitting on top of some soil. Okay? And out the bottom, I have this nice little tube. And I'll have it go down here, why not? Okay. And then this tube, I collect the water from that tube in my little graduated cylinder. So I can see the amount of water I've collected in time. Okay? And that way I can measure the flow through the system. Okay, so let's just follow the total potential in this whole problem. So the first thing we have to do whenever we do a problem like this is we have to assign a datum. And as we've talked about before, it doesn't matter where we put the datum as long as we choose a place and stick with it. So just for the sake of convenience, well, maybe, in fact, what I'll do is I'll put it in a little bit of an awkward place. I'm going to put the datum right here. So I can put z equals 0. At the bottom of my column, it sounds all fine and well, but the water's coming out here. And so we'll have to account for the fact that this is not at the datum. So we have drips of water coming out and filling up our system here. Okay? So let's talk about what the total potential is at these various locations. Okay? So the first thing we can do is let's identify the depth of water that we have ponding with a little d. Okay? And let's identify the height of the soil column with the letter L. Okay? Now, so we have a height of water of D and a soil water column L. That's wonderful. Now, where do we know something about the pressure? Well, we know something about the pressure right here. At the top of the column, there's a water table, and our pressure is equal to 0. Okay? So this is just filled with water, and so it's like a glass of water, just sitting there more or less. So it's static. And so what do we know about the total potential here? What's the total potential right here? Well, Z is equal to L plus little d. And the total potential is always equal to Z plus H. And so our total potential right here, and why don't we call that H with a T, top. H top is equal to L plus D, that's Z, and little h is 0. So it is simply L plus D. That's the total potential up here. Now, where else is this total potential applicable? Since this is hydrostatic, it's not moving, there's no turbulence and moving around of water there, the total potential is the same throughout that water. So this is our soil, keep in mind. And that's our water. So our total potential HT applies both here and here. So it's the same total potential. Very good. Now, we displaced the outlet some distance, and we'll call that, just for use of letters, B. So it's some height B. Okay. Now, what do we know about this location? Well, water is just dripping off the bottom. So what we know is that is a 0 pressure. So our pressure there is 0. Okay? And what is our Z? Z is now equal to minus B. B, since we measure Z from the datum, it's positive upward and negative downward. So Z equals minus B. And so what do we have for our total potential at the bottom? is going to be, as always, z plus h. And I just write that down just because it's just a great place to start. And we're going to say that's equal to minus b plus 0. Okay? Now, my next question is, what is the total potential right here? What is the total potential right at that interface between the pipe and the soil? What we're going to make is a big assumption, and the assumption is that the pipe offers no resistance. So water pours through it easily. That means that, once again, we can take this water in the pipe as hydrostatic. We're not using any energy. Our soil is doing all of the dissipation of energy. It's the stuff that's hard to flow through, and the pipe is really just conducting the water from one point to another. That means that our H question mark is equal to what? Well, if this is hydrostatic, the total potential is the same everywhere. So that is just exactly equal to HB, which is equal to minus B. Okay? And now we have it. If we wanted to calculate the flow through the system, we say, aha, the flow is going to be equal to the negative of the area of our column. So if I drew this little area there, times the saturated conductivity, because we have a saturated column, times the gradient in total potential. And because our soil is uniform, the gradient is the same everywhere, the flow is the same everywhere, so we can say that that gradient is just equal to the gradient over the entire column, which is going to be what? It's going to be the total potential at the top minus the total potential at the bottom, divided by the total path length. Through the soil, and that's going to be equal to what? Well, our total path through the soil is just equal to L, and HT is going to be L plus D, so it's L plus little d minus, which is plus B. So what we see then is what we really wanted to have, which is that we know that as we lower this pipe, it'll increase the amount of energy to drive flow through the system. If we elevate this pipe to the top, there'll be no flow at all. As we drop it, it gets to be more flow. So indeed, as we increase B, the gradient in potential increases. Also, as we increase the ponded depth, the gradient increases, as well as the total height of the column. And so really we can simplify this and say that this is equal to L over L plus D plus B over L, which is equal to 1 plus D plus B over L, showing that had we had B equals 0, had the flow come right out there, and had we had no ponding depth, this would be 1. So the gradient would be exactly 1, which is called a unit gradient. So it's a nifty little way to see how the total potential can be tracked through a problem like this. And we also have this little side benefit showing that when there's water freely flowing through a column with neither standing head nor a suction pipe on the bottom, the gradient total potential is 1. And that's what we call the unit gradient flow.